Hello, in this video I will talk about tension vectors. I'm going to prove a conditional proposition, like if P then Q statement. Okay, so here is the propositions. Okay, so the following we're going to assume for P going to be true, so that gamma, which is a smooth curve, is a mapping from R1 to M, where M is the manifold, such that the dimension of M is equal to n in this case. Okay, so be more precise, gamma of t0 is a point on M. So that's the starting point. And t0 is in the subset I, which is in R1. Okay. And then local coordinate charge is going to be U alpha. Well, U alpha is some open set in M. And then phi alpha is vector value functions from M to Rn. Okay, so here comes the Q statement. So the time derivative evaluated at t0 is equal to vi partial xi evaluated at x of t0. So this here is the tangent vector. It's tangent vector to the curve gamma at t0. And then, of course, the derivative of this curve is the vector that we're talking about. Okay, so here's the proof. This is going to be a direct proof, so it's going to be like if Q, then P. So we're going to assume P is true. So all of this here is assumed to be true. And then through logical steps, we're going to conclude that Q is also true. So let me write down what we have in P here. So imagine you have a curve on the surface, mapped to the surface of the Earth. So it's like a flight from, let's say, from LA to Vietnam or something. So M is the actual manifold, or the path on the Earth. Okay. So point P right there is where gamma t0 is located on M. And then, of course, you have a functions going from M to R1. The composition function from R1 to R1 is just you're going from alpha, R1 to alpha, compose F. So that would take you from R1 to R1. And then you have the U alpha open set around P, in the neighborhood of P. That allows you to map that region into in this case, R2 without any loss of generality. I'm going to let the dimension of M equal to 2. So you have the x2 values and then x1 on the horizontal axis. So when you're on the airplane, you see the TV and your position of the airplane and the speed. what you're looking at is this R2 picture here. Okay. Okay, so to get the coordinates functions, you're going to compose gamma composed with the phi alpha. So that'll give you phi hat. So phi hat is mapping from R1 to R2. Okay. Likewise, you can have the same thing for the functions going from R2 to R1. So we're going to let point Q on the R2 here is equal to the mapping of the point P in M, where M is the actual surface of the Earth. So this is the coordinate presentation for the functions. So it just tells you that it just do the composition of the inverse mapping and function f. So f hat is a mapping from R2, which is a subset of the phi alpha u alpha is subset R2 mapped to R1. Okay. And then looking up here, you see that whenever you have a mapping from R1, in this case gamma, you're going to induce a tangent map or push forward map of a operator. In this case, the operator on R1 is going to be dt, where dt is considered tangent to R1. Okay. So gamma star is going to map d by dt to the tangent space of M, and this object push forward of d by dt 0. Okay, I think we're all set for the start of the proof now. Okay, so this is all P right here. Okay, so here is the proof. So d by dt of f composition gamma at t0 is, I'm just rewriting this in coordinates presentation of this mapping of this functions. It's also equal to the time derivative of f hat composite gamma hat. So you see that the alpha, the mapping, is a vector value function. So it map point P or the gamma curve onto, in this case, two-dimensional coordinates. So at this point here, you could just do chain rules to get to the answer. But first, let me just write down. So gamma hat is equal to, is a mapping from I to R2, which is from here to here. And then you see down here, f hat is a mapping from R2 to R1. Okay. All right, so now you could just do the chain rule, d by dt of f of gamma hat, and gamma hat is defined to be x1 and x2. So this here is just the chain rule. You take the derivative of f hat with respect to xi, and then dxi dt. So that's going to define the velocity. And in our case, it's just 2 dimensions, so I is equal to 1 and 2. So dxi equal to vi, so I rewrite it first, and then partial xi. And then if you remove the functions, then the time derivative operator evaluate t0 is equal to vi partial xi in proof. And then the basis partial xi is going to be the basis for the tangent space of M. Alternatively, we could use the other way. We saw that the curve gamma function, the mapping of the curve onto M induces a push forward map or tangent map or Jacobian map from TR1 to T, in this case TR2. So let me rewrite the picture. So here's the curve to M from R1. So the operator d by dt is in the tangent space of R1. So this is the induced map right here, tangent map. So the T0 get pushed to gamma's T0, which is also equal to P. And so the operator d by dt get pushed forward too. So now this new object here, the push forward of the d by dt is an element of the tangent space R2. And then the Jacobian map of d by dt in R2 is simply equal to that d1 dx1 dt partial x1 plus d2 dt d by dx2. And so now you could apply that linear operators directly on f here. Yeah, so you just let that operator apply on the composition function of f and gamma. is equal to the right hand side where you apply the operator from the TR2 space onto F directly. And then you can also rewrite this as the gradient of the function dotted to a vector v. So the way to interpret this is this thing here is equivalent to a directional derivative of a function in direction of v, because you're taking the dot products of that gradient vector with the v vector. Okay, so end proof.